Hello, this is a dramatic reading of Shot in the Head, a blog by the Stand-Up Physicist, available at science20.com. My work on gravity received a fatal blow in the spring of 2007. A patient, creative exploration in the neighborhood of a deep truth might, and I stress the word might, find an alternative expression to dodge the bullet that killed my original math haiku. This blog tells that story. The cranial trauma was caused by a vector coupling term in the Lagrangian, this J mu A nu. All right. An analysis of the phase reveals that the mediating particles are spin 1. Like charges repel for forces mediated by spin 1 particles. Like charges attract for gravity. And therefore, my proposal violently disagrees with observation. Gravity must be mediated by spin 2 particles so that like charges attract. That's just the way gravity is since day one, actually before Newton. It still worked before Newton pointed it out. Now, a keynote address grade professor, good enough to, talk to the big audiences, delivered that blow in a rather testy exchange of about 30 emails. I have a confession. I did not understand quantum mechanical spin projection operators. I'd spend like 0 time thinking about the current coupling term since it's all of 2 letters long. I got blindsided. Now, nobody was actually born understanding spin projection operators. It would be interesting to know what percentage of folks with PhDs in physics actually kind of know that off the top of their head, that a vector coupling term means the interaction is spin 1. My guess is that the percentage is low, or I would hear a doubtful chorus bringing it up over and over again. So by the end of this this discussion, I will show you the simple bit of algebra that actually explains that rather frightening bit of jargon. So my new bullet dodging expression uses both quaternions and hypercomplex numbers. So I have to take a sidebar over here because I want to explain for those who don't know what the rules are for quaternion and hypercomplex products. So briefly, a quaternion is basically a mashup of scalars, vectors, and complex numbers. And we got it kind of going right there, that top line there, where you've got basically first minus last, innie, outie, and then the cross product. And so you've got the dot product in there, you've got the cross product, you've got stretching the vectors, and of course the kind of product of the two things. Now, hypercomplex numbers, the bottom line there, have actually exactly the same dance partners, but there's not a minus sign in the house. Not even for what I call the symmetric cross term, that thing I symbolize anyway with the circular X. So that all positive sign outlook, I think, might be the reason that gravity only knows how to attract. Doesn't know. Gravity is the universal love force. Woohoo! The strength of that love, though, is beyond pitifully weak, which I think is probably a good thing. Now, how would you use these things? Well, a Lorentz invariant scalar goes into Lagrange density, and one can use either one of these products to form exactly the same kind of current coupling term. So you either just take that J current density and do a quaternion product with the 4 potential, or you use a hypercomplex thing and you got to throw in an additional conjugate operator. That's what that star is, and then you end up with this 4-vector rho phi minus J1A minus J2A, A2 minus J3, A3. That is invariant under a Lorentz transformation. Okay, and that's what goes into the Lagrange density. Now, with these types of products, though, there's also a phase associated with it. Why don't we see everything else? That would be like what would that be? That would be like the stretching, vector stretching terms and the cross things, whether they were symmetric or non-symmetric. So those phases are different. And I'm going to show you that the phases of the quaternion product are for spin 1 projection operator. And hopefully I'll get to show you how using the hypercomplex product leads to the spin 2 projection operator. So how do you kind of go about learning this sort of thing? Oh, let me go get my book. People love it. The book. This is where you go. There. Okay. Specifically, I recommend focusing on good old chapter 3 here. So I actually spent literally a few months looking at about 10 of these pages. I read slow. No, well, when you think, maybe I should say I think slow. I can read the words quickly enough, but the reason is that I struggled between to map 4 vectors. That would be, you know, the currents and the potentials. They have kind of 4 slots, and the complex numbers, which only have 2. I mean, sure, I could do it the standard way taught by this very master. However, I'm kind of like a jerk when it comes to accounting. If one has a 4-vector current, one should use a number that has 4 slots. And that would be the quaternions, not the complex numbers. Well, except that quaternions are 3 complex numbers that share the same real. I mean, it's not like they're unrelated. They're very much related. So what goes into the text, of course, is typical, and it's the accepted approach. But it actually looks to me like a case of sloppy accounting. And we kind of know sloppy accounting eventually comes up to bite your head off, okay? So at one point in this fine text, the current density along the x-axis is treated as a real number, while the current density along the y-axis is treated like an imaginary number. And that sounds like completely arbitrary. I mean, why not switch the roles? Well, there's no reason. And at another point they say, hey, we're going to take this x thing and multiply it by this y thing, and we're going to get an imaginary. They don't say, when I multiply this x thing by a y thing, I'm going to get a z thing, which is what they should do, because, you know, with this kind of current stuff, you've got the cross product working. So you should see the cross product working, right? And so, I mean, don't worry, Feynman gets the right answer. Feynman is Feynman, you know. But I'm going to use quaternions and hypercomplex numbers because the accounting rules, you know, to me are much clearer. You know, there are 4 slots, and when you multiply x times y, it ends up at z, where of course it must, if you're going to be using cross products for everything else, right? So we're going to start with the spin 2 projection operator, because Feynman actually has an incredible reduction of this complicated creature, to actually 1 quaternion product. He was analyzing current moving along z, and one of the effects of special relativity is that it generates virtual currents in the x and y. And a spin projection operator, it actually uses these 2 currents, but makes sure they cancel each other out, because this is just kind of this special relativity thing. So one might be afraid that the math going on here is like really, really difficult. Quantum mechanical spin projection operators. Sounds impossible. All right, well, but Feynman had the insight to make it look like almost trivial. So here is the relevant passage from page 39 of his book, and particularly focus on the stuff I underlined and put a couple stars next to. So he's looking into the quantum mechanical spin 2 projection operator created by virtual currents. And the jargon sounds scary, but Feynman says it's no more difficult than this little bit of complex algebra. X plus minus IY times X plus or minus IY equals XX minus YY plus or minus 2IXY. It's that 2IXY that's really so important in this analysis, because that 2 means this really can be plus 2 or minus 2. Those are the only two possible states here. So to make a spin projection operator, you actually need to cancel that thing out, and so that's exactly what he does, and all well and good. So now we're going to repeat this process, but I'm going to repeat it using hypercomplex products like so. Okay, there we go. So we've got the X in the X position, the Y in the Y position, and we see that, you know, if we flip the signs, we get this minus minus X, minus minus Y, and then in the Z slot, where it belongs, is a plus or minus 2XY. So the product ends up in that Z slot, which is a good thing. And the first term, being negative, actually matches what goes into my current coupling term, which is, again, a good thing. It connects to what's going to my Lagrangian's all about. So the projection operator can be constructed in the line below, where we basically have the 2 pluses and the 2 minuses, and leaving no imaginary part in the Z. All right. So this this expression using hypercomplex products is a way to represent the quantum mechanical spin 2 projection operator. It is different from what Feynman uses, but that's okay, because he was kind of like doing a kind of more heuristic argument. So Feynman actually goes ahead and treats the spin 1 case a few pages earlier, and there it is. It took me actually a while to spot this spin projection operator, because he didn't really write it out in quite the same way. He used these conjugates, and here's actually another way of looking at it, where you write it out explicitly. So you see, instead of being a plus minus sort of thing, it's a plus minus minus plus, or minus plus plus minus sort of thing. So let's go ahead and do this, and this time we actually have to use quaternions. Okay, so here's the quaternion expression. Okay, so we've got the xy, and I broke it into little parts so you could see it happening, because the first one gives you a minus x and then an xy in the z position, and then the second one gives you minus y squared and a minus xy in the z position. And so together, when you add them up, of course, you end up with a projection operator, because it's got no imaginary thing in the z. And it's spin 1 because there's basically plus 1 or minus 1 can be that in the z position. So that's how I do a spin 1 quantum mechanical projection operator using quaternion products. So here's my recap for those keeping scores on what's in my actual Lagrangian. So the first line is for the Maxwell equations using quaternions, and you can see we use only that x there, which I'm using for the quaternion product. We've got some subtraction thingies going on there, which is to make things gauge invariant under a gauge transformation. And then the middle line is my Lagrangian for gravity, and it's basically swaps in the hypercomplex product wherever there is a quaternion product. And then when I unify it, I'm not just adding these two together, but I'm getting rid of that subtraction step, which was key to making it gauge invariant. Here it's gauge invariant because they have the same gauge dependencies, and that's essentially why I think there's no need for the Higgs. So all three of these Lagrangians are gauge independent, although The third one is interesting because the two separate terms are gauge dependent. It's just their gauge dependence exactly cancels. Now, in the art world, a typical museum visitor spends about 10 seconds looking at a painting. The artist might have spent months or years creating the work. And so, aware of this behavior, I actually revisit pieces, look at them from different angles, and try and get my eyes to really see it. And I feel the same way about that triptych of Lagrangians. I like to see the spin not only in the current coupling terms, but in the field strength tensors as well. And you can get a sense of that by rearranging things and seeing what happens. If you rearrange it with the Quaternions, the signs flip around. If you rearrange things for the hypercomplex, they don't. The most fun, though, is trying to embrace the big picture. The kind of like, what the fuck does this all mean? Okay? And my sense is that the Lagrangian represents an exhaustive accounting of all the ways sources can play with potentials using multiple ways to multiply. And you're looking at all the ways that a space-time potential can change in the four directions of space-time. And my mind just will not actually be able to appreciate all of those moves that nature has. I feel confident that the hypercomplex vector coupling term spins away from the spin 1 bullet. The gem Lagrangian requires no Higgs boson. And here's actually one person's guess as of July of 2011 about my odds of succeeding. For the 30 to 140 GeV, the possibilities are: 1, it's just bad luck. It will disappear in the next round of data, which we will know in 2 months. 2, it is the standard model Higgs. Or 3, it is a Higgs of a model with more Higgs bosons. My personal guess is number 1 is 30% likely, number 2 is 30% likely, and number 3 is 40% likely. The next big conference is August 22 in Mumbai. There will be a lot more data then. So I actually like the math in this post. So I like my odds at 30%. You know, physics may get blindsided by Quaternions and hypercomplex numbers. All right. Thank you very much.